Okay, just a little bit more to finish up our introduction to forces. And just going back, because at the end I thought I was going to run out of time. So while that was uploading, I found my FX from case 4. It's 346. So this whole length now across the bottom would be 646.41 newtons. Up the side is 200 newtons. So you would square them, you would add them together, you would take the square root to get this length, and then you would find the angle. Okay? A couple other things I didn't say about this. Obviously, if you want to get the biggest possible net force or the biggest possible resultant, you would add them together, right? And when you add them together, this was when the angle between them was 0 degrees, and that will give you the maximum resultant, right? If you're trying to move something and you both push in the same direction, you're going to get maximum force out of it. These two vectors are 180 degrees apart, and when you're totally pushing opposite each other, it's going to give you the minimum resultant, the smallest possible force, because you're working against each other. Okay? And because what that tells us then is if you're pushing at 90 degrees, which is what the third case is, or any other angle, then the resultant that you get must be between the maximum and the minimum. Because if it isn't, then one of them is in the maximum or one of them is in the minimum. Okay, and what I mean by that is, let's suppose I say F1 is 12 newtons and F2 is, I don't know, 10 newtons. And then I could say, is there any way that these two forces could act together to give me a resultant of 24 newtons? Is F net ever going to be able to equal 24 newtons? Well, what you would do then, you would say, well, adding them up to get my maximum resultant, that would be 22. And subtracting them to get my minimum resultant, that would be 2. Since 24 doesn't fall between 2 and 22, these two forces can never produce a resultant of 24. Could they produce a resultant of 18? Yes, because their minimum is 2, their maximum is 22, 18 falls between them. So at some angle, we could get a resultant of 18. We don't care what the angle is, it's just more, could you get a resultant of 18 by somehow putting these together? And so if it falls between their maximum and the minimum, then it can. If it doesn't, then they can't. Okay, and so the last thing I want to talk about for just a few minutes is something that's called the equilibriant, or the equilibriant force. And it's a force, let me draw it out. If we were in class, I would take a person and I would have someone pull on one arm with a force this way, let's say 100 newtons. And I would have someone else pull on the other arm with a force this way, let's say 200 newtons. And then maybe I'd even have a third person pull on a leg, may as well keep going, with a force of 300 newtons. And the person here in the middle is feeling kind of torn. Get it? Torn. But if I didn't want that person to move, then I could put a force on the person this way to prevent them from moving. And if I wanted to prevent them from moving, this force that I'm exerting would have to be equal to, but opposite, the sum of these three forces. So I would have to find the resultant of these three forces, and then the F I would put on would have to be equal and opposite. Maybe it would be easier to see if I had the people pulling in the same direction, right? So if you had F1 going 100 newtons this way, F2 also going 200 newtons the same way, and F3 going 300 newtons. So now they're all in the same direction. Let's say they're all east. What would the equilibriant force have to be to keep this object from moving? So the rule is you add them up. 100 plus 200 plus 300 is 600 newtons. This would be the net force, the resultant. And the equilibriant force then is equal but opposite. So FEQ So this would be 600 newtons east. So FEQ would just be 600 newtons west. So I would have to pull with a force 600 newtons in the opposite direction to keep the object in equilibrium. Okay, so a definition of equilibrium is a force that is equal in magnitude, in other words in size, equal in magnitude, and the word magnitude just means size, equal in magnitude and opposite in direction. Opposite in direction to the resultant force. Okay? And as a result, it keeps the object in equilibrium. Keeps object in equilibrium. Equal in magnitude and opposite in resultant keeps the object in equilibrium by canceling the resultant out, right? If they're pulling with a total of 600 newtons one way and I pull back with 600 newtons the other way, I'm canceling out their 600. So by canceling out the resultant. Now when we keep something in equilibrium, it might mean that it stays at rest, but it could also mean that it'll keep moving at a constant speed. And what I mean by that is like this object, imagine a cart rolling down, rolling across the floor. It's rolling and you want to make it roll faster, so you push with a force of 20 newtons, and I don't want you to make it roll faster. I push with a force of 20 newtons in the other direction. The cart will keep rolling because we're just canceling each other out. The cart would only change its rolling if one of us was pushing with a bigger force. Okay, so that's equilibrium force. And that's enough of forces for right now. We'll come back to it the next day. I see you.